Yeah, so it's a great pleasure to be here. And in today's talk, I'm going to talk a little bit about how two different fields initially at first glance should come together actually to create AGI actually, to create the future of AI. So here I use the term AGI in the title, but just to be clear, I don't mean it in the philosophical sense or the controversial sense. It's just a nice abbreviation to mean AI systems that can generalize across domains. No more than that, right? So it's strong AI versus narrow AI. So first, talking a little bit about AI and communication for those of you who don't know. So there was a love-hate relationship between the two. Like at the time of 4G, everyone in the networking community hated AI. So when I used to present then, they used to shun me and say, no, this doesn't work. And then in 5G, things became a little bit better because we had some sort of this IoT. And in the IoT, you need some sort of AI at the very least for network management. So there was some tolerance for AI at the time, right? And in 6G, now everybody loves AI. And 6G system is officially called an AI native system. And now we kind of want to know what does that really mean. So after this talk, hopefully you don't go back to not believing in AI. So this AI native wireless system is what brought, in this talk, it's a little bit more of a thought process, and I'll show you some results as well. But how we came to the kind of realization that AI native systems are basically a doorway into actually also creating AGI, and I'll get into that later. So how do we get into AI native systems? I'll do a quick glance on wireless. I know that some of you don't know much about it, but you don't need to. In the talk, there's very few things that are wireless. But the core question we need to ask is not, will it be AI native or not, is which AI do we need? So what are the features of the AI that will work well in networks or in any system that is dynamic, where there's a lot of agents, where you have heterogeneous environments, and where you need to adapt to a lot of things in a quick manner. So some of the features we need in communication and in others, I think. Explainability, of course, and everybody knows about that. So in wireless, if you think about it, you cannot deploy any model in a mobile phone or a network if you don't know how it works, because we need performance guarantees. Second, it should be reasoning based. We cannot still rely only on learning, because again, not a lot of data is always available. And of course, when you think about communication data, it's very private. So we should be able to do reasoning outside what can be learned and trained on. It should be also generalizable in the sense that you can transfer skills, and I'll get back to that. Distributed and green, that's not part of my talk today, but these are important features. Also continual learning. So my talk today will focus primarily on the left-hand side, specifically reasoning and generalizability, because these are the path towards the future of AI and communication systems. So this is the slide where we show a little bit the evolution of these two kind of different technologies, wireless on the right-hand side, and AI-based networks, if you wish, on the left-hand side. So 6G was supposed to be an AI-native network, and there are some advances towards that, and primarily they use statistical AI. So the tools we have, off-the-shelf tools like autoencoders, diffusion models. Now, of course, all the hype is on LLMs, but I don't know how LLMs can control a network, but that's a different story. And then there's the evolution on the communication side, so adding more antennas, improving the physical layer, creating new multiplexing schemes, and so on. So the question for us is, if AI native 6G should be target for us is 2030, it will, as far as we can see now, it's still reliant on statistical AI. It's not really AI native, in my opinion. It's just slapping AI in a few functionalities of the network and making it work, which is fine, but that's not what we want. We want it to be native, meaning that the network itself is built through AI system, and that requires many of the advanced AI tools we're seeing now, which is causality is one thing, and I'll talk about it later. Neurosymbolic AI, I'll touch on it, and something called semantic communication, which, in my opinion, is a way to create AI native systems, and I'll mention it later. So these are, generalizability is important, planning, reasoning, and problem solving. So we need AI that can not only actually solve problems, but also pose the problems, especially when it comes to communication networks. So this will allow us to create, moving from this advanced AI towards AGI, will allow us to create some new applications like cognitive avatars and, metaverse experiences and all that. But that's, again, outside the scope of what I want to talk about today. So the question for us is, how do we go from here into here? And what is the relationship between communication networks and AI? So in order for us to understand why would someone in networking be interested in AI? So if you think about it, existing systems in networks, there's a lot of ways we can improve performance, meaning rate, reduce delay, and so on. One is you add more spectrum. Another is you improve computational complexity. Another is you kind of create, again, more antennas and so on. But all of these are limited by physical limits that we know, the Shannon capacity, computational complexity limits, electromagnetic limits, and spectrum limits. I mean, at the end of the day, there's only a certain amount of spectrum. What AI allows us to do is, of course, not break the physics, but better manipulate it to do more with it, right? So I show it here just as an illustration. We're still limited by Shannon's capacity, but we can fit in more stuff into that capacity region. So that's what we want. And this is what reasoning and planning already allows us a little bit to do, because if the network is able to plan forward, then it can better use its resources. If it's able to reason outside the data, then it can adapt without the need for continuous feedback. But that's not enough, right? So it still doesn't deal with unforeseen scenarios well, and it's not full generalizability. So what is the missing link here? Turned out, we had to go back to AI and see, what were people thinking about in the early days. And people were talking a lot about common sense, right? So common sense is a feature that we wish to have in AI. All the discussions have been more or less philosophical. Early on, they tried, but there was no computational ability to actually define it. But I'm going to tell you what we mean by it and how common sense now comes into the picture. So to define common sense, you need what is known as a world model. A world model is essentially understanding of or a representation of the system you are managing. If it's a communication system or the real world, either way, it's fine. Right, so what happens to AI native networks? So in my opinion, to go from AI native to AGI native, you have to have common sense, and I'll define it in the next slide. Again, reasoning and planning are still there, but they should be a part of the common sense. So what is common sense, at least for us, right? So what are some of the features of common sense? One of them is analogical reasoning, which is the ability to kind of learn what to do by analogy. For instance, if I learn how to open a door, and you give me a window, I have some sort of a way to open that window, right? Even though I didn't really learn that window. Second, dealing with unforeseen scenarios, which is in AI terms, it's horizontal generalizability, right? So we need to be able to do domain out of domain, handle out of domain corner cases. And filling in the blanks, for instance, an example here, very illustrative. If you see someone following you in an alley and it's a dark alley and you have money, then maybe he's gonna kind of stab you. So there's some fill in the blanks that our brain does, and AI systems don't do very well with that. So this requires some logical reasoning, right? So grounding in symbolic AI. In some sense. And the more interesting but the more difficult part is the intuitive physics. So can the AI learn high school level physics so that it can know, the trajectory of this paper airplane? In some sense, it will go into the trash can, right? So if you throw a glass on the floor, you kind of know it's going to break because of physics. Can we learn those intuitive physics? Now, it turns out that some of those ideas were a little bit being developed and are being developed, actually, by Yann LeCun, but we have a little bit of a different and synergistic view on that. So he has this vision of, he calls it advanced AI. It's AGI or advanced AI, it doesn't matter. And he has this a model which came from neuroscience, where you have a perception module, an actor, and a world model, of course, and world models are important, and I agree with that. And the perception comes from the real world, and then you can create a world model, use it with the actor. Of course, there are costs and memory, but that's beyond the point, and then kind of act in the world. But for Yann's case, he looks at it from the perspective of a single agent. And if you think about it, a single agent cannot have a view of the entire world. Right? It has a narrow view of its world. So the fact that you say a single agent must know the entire world is very difficult, which is why Yann, he kind of knew that, and he defined a configurator. But he said, I don't know how that configurator works. He just said that it can focus on one part of the world, given the wealth of information. Now, this is a bit of an issue, because the configurator is not really something we know how to implement. Second, if you have multiple agents, which world is correct? Are they consistent? So how do you build a world model at the agent level? It doesn't kind of work very well. Turns out that the network can do it for you in some sense, because if you think about it, in a communication network, you already have, for those of you who are in this area, you know that future 6G networks can not only do communication, but also sensing of the environment. So they can give you information on location, on how you move, and so on and so forth. All this information can be sensed, and that could be an input to a perception module. Now, the perception module, what does it do, for us at least, in what we call an AGI native telecom brain, is basically create a representation of the world just like the brain somewhat does, a representation that kind of has the essence of the world, and that representation is then put into a world model. So the world model for us is, think of it as a digital twin. So it's a digital twin of the actual real world system, where we have two foundational aspects. One is causal model, second is hyperdimensional computing, and I'll get to that later. And this world model, which is basically on the network now, can think, right? So it can think of future plausible scenarios, and then it can go back to do action planning as well, which is which is what you need, right? The action planning could be changing the beam of the beam direction, or asking the car to move. So there's actions taken in the world. Think of that as a control loop, right? So the action is back to doing control. Now, the question for us is, how do we build the perception module? How do we do abstract representations to create a world model? And of course, how do we do action planning? For the scope of today, I'm just going to focus on perception world models, not on action planning, so I'm not going to talk too much about it. Of course, sensing is another challenge, but again, no time for it today. And in fact, doesn't need much of AI. You can use AI, but it's not the main thing there. So let me focus primarily on perception and how that feeds into a world model. So what is a representation? What is an abstract representation? So let me start with that. Abstract means it summarizes the real-world elements by removing non-essential data, right? Like if you want the outline of a chair, you don't need to know everything about that chair, right? And it's a representation because it encodes those real-world elements into symbol representations. If you're in the networking community, these are not the symbols we send on the channel. These are just symbols to represent the world. So sensing, of course, is a precursor, and I'm not going to go back to it. And this will allow us, with abstract representations, I can do analogies, right? Think of the door window example I gave before. So how can we abstract the physical world? We need to disentangle the information in it, which we call the semantics. So in communication networks, semantics is the meaning of a message, and this is the meaning of a real-world element, right? And it's related, but not the same as semantic segmentation. It's kind of, they're related, but not exactly the same. So we can do that, and we've shown before that you can use contrastive learning to basically take, for example, the picture of a dog and separate two types of data in it. One is learnable data. This is where semantics exists. This is where structure may exist. And spurious data. For example, for this husky here, there could be a dot on his paw. I don't need to represent that. I mean, that's not something we need to represent. On the other hand, the outline of the dog, yeah. And then there could be two options in the learnable data. One is structure. It's a dog. Second is variability, which is really, it's a husky. It has some special features. And these are what we're going to call the semantic content elements, and they're represented through some sort of a ZI, and I'll get to it later. But at the end of the day, the question for us, okay, we found learnable and spurious. Again, contrastive learning can help you do that. And there are other methods as well. And then the question is, how do we encode those abstract representations? What characteristics should be considered when we encode those abstract representations? And this brings us into encoding. So abstraction, we already talked about it. We need the essential characteristic. Generalizability, as I mentioned, we need to have a common form. For instance, when I say dog in Korea, it's the same as dog in the United States. And the third part, which I'm going to discuss more, is causality, right? We need to look at not only statistical relationships, but also causal relationship in the data. So causality, if you know about it, if not, this is a quick primer, is the idea of discovering causal structures in the data. So the first step is a causal discovery step. One way to model it is through a SCM, which is a structural causal model, which is like something like this. It's a directed graph where you have the variables in the data that cause and effect variables, and there are some randomness coming from outside that cause and effect graph, which could be like, for instance, in the network architecture impacts the channel is impacted by the frequency, and so on. And then once you have the discovery, then you can represent you can represent this large dimensional space into lower dimensional causal variables, and then you can do causal inference, meaning you can fill in the blanks, if you wish, inside this SCM. So if you go back to the origin of causality, so in one of the famous books by Judea Pearl, he says that there's 5 or 3 levels of reason or logic. So at the bottom level is what we do today, statistical ML, which is pretty much all the AI you hear about, even LLMs. They're just doing statistical correlation, basically, right? And that's fine. There's nothing wrong with that, and that's associative logic. But on top of that, you can ask questions like what-if questions, right? What if the semantics are different? What will it change? And these are called interventions. And that's interventional logic. You can also ask why questions. Why am I seeing this dog in this picture, right? And these are counterfactual logic. The 3 of them are called reasoning, right? So I mentioned reasoning before, at least in the causal perspective, in the causal framework, this is what it means. So now look at the big picture here. So I have the data sensed. Then I separate structure and, or learnable and spurious. So the white part are spurious, I don't need them. Then I go back, I have semantic content elements. They can create a structured entity now, let's say a human, which could be a man or a female. And then you have, it's interesting that, of course, there's no one-size-fits-all solution here, because there's a kind of a tension between causality and generalizability. If you find all the causal variables, you're kind of overfitting, which is great for prediction, right? It's great for faithful prediction, and basically you get higher reward if you have, let's say, an agent, but it's bad for analogical reasoning because you're not generalizable enough. On the other hand, if you do less, then you're generalizable, simple to predict, you can do analogical reasoning, but your predictions may not be faithful. So there's a trade-off to be optimized, and this is a general form. I need to find the representation that maximizes my reward, whatever that reward is, minimizes the prediction error, and minimizes the generalization error. And that's not a trivial question, right? So I will show some results in some cases, but there's no general form for these equations. So now I'm going to move from symbols to something that allows me to represent the physics, right? And physics in the simplest form could be vectors. But now I'm in symbol space. So to move from symbol space to vector space and create a world model, then I need to do some changes. So now why do we think of hyperdimensional vectors? Just because, again, high school physics and the real world can be represented by certain large-scale vectors, and hyperdimensional vectors are a useful way to do it. It's not the only way. It's a useful way to do it, and it allows us then to represent this intuitive physics element of the common sense. But as I mentioned, I have symbols, and they're not vectors. So this is where, and I'm a big advocate that in AI, it's a black box sometimes, but we need more math if it were to work well. So we need to look at basically go back to topology theory, and there's this big framework called category theory, which allows us to, in this particular case, to move from symbol category, where you have, let's say, this blue and red, they are kind of connected by a morphism, through a functor, I can actually disentangle or basically take the features out of the symbol, and these features are now vectors, and they can be represented as a hyperdimensional vector. So why is hyperdimensional vector useful? There's three functions that I can do now that allows me to basically understand a little bit the physics. One is binding, which means if I have direction to the right and or direction of movement and right, I can bundle them. I can bind them to have direction of movement to the right. You also have bundling. You have tall man and direction of movement to the right. You can bundle them to say the tall man is moving towards the right. And there's permutation, where I can actually understand over time what is happening in the world. So these are some way to look at it. Now, once you have the vectors, you can take actions. As I mentioned, I'm not going to talk about actions because I'm going to show you some results on using world models or causal world models in context. So this is just how it looks like. So you have now a representation of the vehicle, of the asset, which in this case is just the road, and of the humanoid. I have a causal random world effects. I can have actions for the network, and I understand the natural evolution of the world through structure, causality, and hyperdimensional vectors. So again, action planning, I'm going to skip it and I'm going to go directly to an example. So this is an example. It's a silly example just to illustrate, and then I'll show actual technical results. So let's say you have a car moving, and there's a dog that's stuck between the car and the beam. Of course, the dog doesn't stop the beam. You need something larger, but just for the sake of the example. So in a regular AI, this will not work well because this base station was trained on data. There was no obstacle there. And it doesn't understand the physics, so it will not really foresee that the dog will block the beam. So this will not work well. You need retraining, and it will work, but it will need time. On the other hand, if you know the intuitive physics, then you understand, oh, this dog is going to come to the car, then you can move the beam away from the car. The second example is on analogical reasoning. Here, even the concept of a dog doesn't exist. So the dog jumps in front of the car. What happens here? It's going to crash. I've never heard of a dog, so that's not going to work. In this case, well, even if the AI didn't hear of a dog, if it had a representation of the world, it may have seen a cat before or some sort of a pedestrian. And then it will say, oh, yeah, there's an obstacle here. I have not seen it before, but I've seen something similar. So I'll ask the car to move away to avoid the crash, and I will update the beam. So One application for all of this is what is known as semantic communication. And simply said, in a communication system, when you send data from a transmitter to a receiver, you're agnostic to the information. And this was thanks to Shannon's theory in the 1948, which, thanks to it, all of your mobile phones work today. But even at the time of Shannon, people were saying, what if I know something about the messages? But at the time, it was very difficult. There was no AI, so nothing happened with that. Semantic communication, in my opinion, is to bring in the abstract representations as semantics, and now be able to have, instead of a transmitter and receiver, a teacher and an apprentice. The teacher actually uses the world model. It doesn't send everything now, bits. It just sends you a representation, just like I'm doing now. I'm not reading the paper, right? I'm just telling you some key points from that work, and then you can fill in the blanks because you have a generalizable brain. And this is what we're going to do here. The apprentice will fill in the blanks. So what is the implication to communication systems? This means that in an asymptotic case, which of course is not real world yet, even if the network doesn't exist, this receiver can work on its own because it can just think and has plausible information. It doesn't need any input from the teacher when the teacher is not available. So think of satellites. When they're not there, then I still can work because I can wait for it. I know some information. Now, this is not crazy because that's how human communication works. We actually manipulate each other's brains and through questions and answers, so somewhat through causal structures. So some results. So first, TWC paper here, we looked at a simple model, just one teacher, one apprentice. We had a world model where we extracted these ZT, which are, SI, which are ZT, which are really just these causal variables that I mentioned before. And then what we wanted to do is we wanted to encode those into a language, right, that allows a semantic language based on the representation of the world that allows the transmitter and the receiver to speak with each other. And the receiver can not only recover what was sent, which is what current networks do, but it can also do phi of z star, which means does some logical operations. For example, prove a theorem, right? It can do some sort of logic, propositional logic on the information it gets to take an action. Now, there's 3 color coding here in this figure. One is pink, one is purple, and one is green. Green is symbolic, so we use symbolic logic to actually do the reasoning. And red is neural, where we use neural networks to actually do some sort of extraction, like the semantic string extraction. We particularly use logical neural networks and generative flow networks in both cases, and we use symbolic logic as well. And the purple is game theory, and I'll tell you why. So there's 2 problems to solve here. The first one is I have the syntactic space, the space of all elements, and I want to represent it in a smaller space U. So I need to create the language, and this is where game theory comes into play. Second, I need to do reasoning, right? And this is where generative flow networks and causality come into play. So 2 problems. Language problem, which I'm going to solve with game theory. And on the right-hand side, causal reasoning problem, which really is using, in a clever way, basically, generative flow networks and basically propositional logic. Now, I'll focus a little bit on I'll give you a little bit more on the math on the language problem. So we have a teacher who's trying to maximize the amount of information it sends, or basically minimize the amount of data it sends, but maximize their semantics, right? So there are 2 different things. And the apprentice is trying to maximize the relevant information it's getting. There's, of course, a constraint because you cannot, to minimize the amount of data, you can send nothing, right? But that gives nothing to the receiver, right? So there is a trade-off. There's something which is the surprise, which I need to minimize, meaning I need to get relevant information. And there's the computing and communication cost. Turns out this problem is a game theoretic problem because you have 2 optimization problems that are coupled between the transmitter and the receiver, or the teacher and the apprentice. And for the equations here, I don't show them here, but to quantify semantics, we use something called, again, I mentioned it before, we use category theory. Actually, we show that the semantics can be shown in topological space, can be something called a copper sheaf, and then we use that to mathematically find the results. If you're familiar with the Carnap and Bar-Hillel theory of semantic information, this is a more general version of it. So what's interesting is if you're familiar with game theory, you need to find an equilibrium. And here it turns out there's 3 equilibria. First one is you send everything with one word, doesn't make any sense. Second one is you send everything with everything, that's kind of against what I wanted to do. But the third one is interesting. The third one says you can find an equilibrium where you have less language being used than the actual syntactic space. And that equilibrium in 2-dimensional space is nothing but a Voronoi tessellation, but can be generalized to n-dimensional space, no problem at all. So some simulation results. On the right-hand side, it's a quick one. We're really better than anything existing in the literature. Some people use it just probabilistic logic, other use KL distance. We're better in terms of reliability. We're better in terms of how fast we get to that reliability. On the left-hand side is an interesting chart because it shows a little bit of a trade-off. You need some time to learn, right? This is not free. But you can see here I have like 4 tasks that are consecutive. Task 1 takes about 30 iterations to learn. Task 2, well, it does it with 23. And then we go down to 17 and 12. This means because I'm generalizable, I understand the world, I can do faster. And a final quick result before I wrap up. So what if you have an actual digital twin that is built at the base station, like a real complete digital twin? So in this case, we looked at the case where, let's say you want to control a robot in a factory. So you're trying to understand the world and send some data through semantics to the robot. The robot needs to execute basically what you're doing at the base station, but there's a discrepancy between the two. So here we combine imitation learning with semantic understanding. And we basically use, again, I think I'm a little bit over time, but just a few minutes to wrap up. So we use something, we need to find what are the meaningful information, right? Instead of doing contrastive learning, here what we used is something called integrated information theory, which comes from neuroscience, which allows you to understand how much information is there in a cause and effect structure, right? And we can quantify it, and then we can go from the entire data to just some semantic content elements that are of relevance to us. And in fact, we can prove a lot of things. Without the math here, I just show you what they are. So we can show that the error is, the error between imitator and an expert depends on the posterior of the confounding variable. So we really need a good estimation of those. The structure, what's more interesting, the cause and effect is a simplical complex, which means I can do a lot of proofs because now I'm working in a simplical complex. I can show that the semantics are abstract cell complexes, so they represent the meaning. I can also quantify semantic reliability, semantic similarity, and all that stuff. We can also show that the discrepancy in the transition probability dominates the error, which means I need an accurate physical modeling, and this is where some sort of Gen AI can also help. Also in simulation, on the right-hand side, again, we show that we're better than transformers, so we can do a lower symbol error rate, which means higher reliability. On the left-hand side is the more interesting, again, result. It's a case where we disrupted the system at, sample 6,000. And of course, both the transformer and our approach will eventually cope with that. But look how long the transformer takes. I did not really complete it. But you can see our approach immediately, there is a disruption, but it immediately adapts to that. And that is important for networks and for dynamic systems. And the only way you can do that is if you have a sort of a world model that governs your system. So we want to move. What do we want to do? We want to move from data-driven networks, which were really from the late 2000s, or early 2000s, sorry, to information-driven networks, which is what we have now. So today in networks, we have some sort of relationship between the data points, which we call information or age of information is one metric. Then we need some knowledge. We need to organize the information to get into reasoning, where we can make basically logical conclusions out of the data. So with that said, of course, there's a lot of things still to do. So we need to move to AGI native systems. We need to stop slapping everything the AI community does, like LLMs, autoencoders, and autoencoder-based networks or whatever, and actually think about the connection between the two. Remember, the missing link in this idea of a world model is actually the fact that the network can build a world model. And second, generalizability and explainability are necessary. Causality allows some explainability. I didn't go too much into that. Energy and computing and all that, that I didn't discuss today, but that's very important. Of course, the physics part is challenging, right? HD vectors are one possible way, but it's not the only way. And finally, acknowledgement to my student, Omar, and Christina, former student Christina, who did some big part of the work, Christo, my postdoc, and many others. And thank you. I'll take questions.
Thank you. So thank you, Professor Walid Saad, for your great talk. If you have any question, please raise your hand. Any questions? Okay.
Yes.
Based on my understanding in the semantic communication, for example, if a user wants to send an image of, let's say, text 1, and if, for example, based on my knowledge, if everyone shares a same decoder, then then some of the receiver might interpret as a, let's say, a bar instead of number 1. Do you think it is necessary for all of the receiver to have their own decoder?
I mean, typically they do, right? Because typically they're separate devices, so they have their own decoder. But one of the points here is that they might be trained differently, so I agree with that. And that's where there could be the idea of having a network that may actually poke them like the imitator expert. It will help in overcoming some of those errors, because if there's an error, then you need some sort of an additional input. But the short answer is they need their individual decoders. A joint decoder will require overhead, and instead of a joint decoder, maybe a network control, just a limited type of network control is enough.
Thank you.
Any other questions?
Thank you for your excellent talk. Okay, I have one question for the Shannon capacity in 6G. So that you expect that is some measuring some kind of physical some media for the 6G?
So I think at the physical layer, there's very little we can do. I mean, if you even listen to talks at CTW, which are the communication theory folks, they say we are within 2 dB of the Shannon limit. So yes, there are people doing MIMO and all that, like gigantic MIMO or whatever they call it. But I think without AI, there's not much we can do more. I mean, we can play, but there's no contribution in some sense. So yeah, at the physical layer, there's very little you can do without some sort of AI or to kind of like just change the way we communicate.
Okay, thank you.
Any more questions?
Thank you, Professor Walid, for your great talk. My question is regarding on semantic communication. And yeah, many research papers refer to just image compression concept as a semantic communication, but you were dealing with different aspects. Yeah. But what is your opinion on that?
Yeah, I mean, they're two completely different things. So I know that semantic communication in the mainstream is joint source and channel coding, which is fine. I mean, you put an image like a deep learning and you learn from the image. But here we're just saying I mean, maybe the term is you should call it something else to avoid the confusion. But we're saying that you need to create a world model and a representation of the world, and that is kind of at a higher layer, not layer in the Aussie layer, but it's a higher level of communication between the two. So the basics of joint source and channel coding remain there. But I'm doing things before that. So I'm doing this semantic learning before that. And then you can still do joint source and channel coding, but I'm giving you basically the world representations, and you can do whatever you want with them.
Thank you, Professor.
Any more? Okay, then thank you, Professor Walid Saad, for your talk again.